Hello, friends. Welcome to the ATC Double Cut. I have a special guest with me today. It is Henry Q joining from Hong Kong, but you're based in Boston right now, aren't you, Henry?
That's right. Yeah, I'm traveling a lot in summertime.
it's, it's I often travel. I happen to be at home today, and when I found out that you were in only one time zone away, I decided let's go ahead and try to set up a call where it's easy for us to talk. So thank you so much for joining me.
Thank you for having me here.
Now I was just watching this morning. I'm gonna share my screen, and let's see. I'm gonna share. I think, yeah, your presentation last year at the crop science meeting. So you have a PhD from Rutgers, is that right?
That's right. Yeah, I spent 5 years of time growing tall fescue and doing models to predict what they look like.
So you have an extensive modeling, and we're not going to watch this video, but I watched it this morning. I'm going to put a direct link to it in the show notes. For those listening, I'm showing a page that has a video from the 2023 ASA, CSSA, SSSA International Annual Meeting. That's the American Society of Agronomy, the Crop Science Society of America, and the Soil Science Society of America. Their annual meeting where the latest scientific research is presented. And you gave a very good presentation on something called the title of it is On the Data Analysis of Small Plot Field Trials in Turfgrass Science. And that's about NTEP data analysis, which is the way that in the United States that new turfgrass varieties are evaluated all over the country. And you're involved with this project can you tell us what you're working on with NTEP?
Sure. Yeah, I get to know NTEP when I started working with turf grasses. That was a long time ago, and then over the years, um, I have learned that there are issues with the existing data analysis and interpretation at NTEP. One of the main issue related to the measurement process that we have for the cultivars. So if you are not familiar with how cultivars are being evaluated at NTEP, they are basically visual inspections. That is, we assign breeders or turfgrass scientists to walk through the plots that are grow into um, 1 meter times 1.5 meter or 3 feet times 5 feet small plots and assign a visual number, a visual rating of 1 to 9, where 1 represents the uh, the bad turf plots and 9 represent the good turf plots. And in such way, we can get people's opinion on the cultivars. However, the issue behind this process is that my ratings are probably going to be different from yours. My for the same plot that I give a 3, you might give it be a 4. Other people might give it a 2. So how do we cannot just simply combine those numbers and generating an average. We have to think about how to adjust the rater bias in this process. And additionally, what I want to address or what I want to emphasize in this process is a problem of 2 dimensions. There's a spatial dimension, and then there are 2 levels of spatial dimension. On a micro level, we need to think about it within the trials. How do we address the within trial variation? On a higher level, on a macro level, we need to think about how to align, the evaluations in one location versus
Okay,
the
good
other.
morning, everybody.
Oh, sorry.
Sorry,
Um,
I was going to scroll ahead to show some of the spatial stuff,
oh, um,
but without the audio. Sorry for interrupting.
that these are the the within trial variation that I'm trying to showcase. There's a better plot either maybe before this, I think. Uh,
Do you want
but
to
at
show
the
the
same,
dollar spot one?
that's right. That's right. Yeah.
Yeah, this one.
Like, yeah, exactly. So these are the issues that we have. This is one example I gave in the talk. That is for 2 plots, 1 and 2, which have
Oh,
about the
Henry,
same.
can I interrupt for a second? a lot of people will be listening to this and not watching. So let's describe what you're looking at with plot one and plot two also.
That's right. Okay. Yeah. So what we are looking at right now is a dollar spot trial conducted at Rutgers. Here, I give you two examples of two plots that look about a similar quality. However, one is surrounded by mostly good quality turf, whereas two is surrounded by heavily infected plots by dollar spots. Although one and two have a similar visual ratings or similar turf quality in this case, I would value two much higher than plot one, just because of the disease pressure, the local disease pressure that two is dealing with than one.
Yeah,
But
that
how do we identify, that kind of level of differences is something that we have to deal with in statistics and modeling. You know.
yeah, and so I'm going to encourage everybody to watch that presentation, which I'll put a direct link to. I found you really explained the problem quite well, and you talked about the issue of. I mean, that's a very good issue. The plot number two there, it's surrounded by plots that are completely infested by dollar spot. Like you almost couldn't find a square centimeter within those other plots or with two of those adjacent plots that are not infected with dollar spot. And yet whatever variety in plot two is, there's sharp lines at the border edge where it does not have dollar spot and it looks like a fungicide. I don't know. Is this a variety trial or a fungicide trial also?
This, in fact, is a fungicide trial, but I want to use this as an example.
Okay. So the if and it looks like a fungicide trial because it's so sharp. And this is the type of thing that statistics can help figure out how or data analysis can help us to figure out how much more weight should be given to the plot that's surrounded by the disease or not, or
Or
yeah, and it's why I think you're familiar with the randomized complete block design, which is the standard way of doing agricultural field experiments, or it had been the standard way of doing agricultural field experiments, and then a lot of small plot research when people are looking at the effect of potassium fertilizer, for example. When I did my PhD research at Cornell University, I
mm,
designed on a L93 putting green. I
mm,
designed a randomized complete block design, which means I assigned the treatments at random within blocks, and I had block one, block two, block three, and we repeat those treatments. And why are there different blocks? Why are the same treatments repeated? It's to account for the spatial variability. But it doesn't work quite properly because you can have gradient. You can never get away from that spatial variability, and sometimes it can't be fit within the blocks. And there's been a lot of research about this. And now you're using some really state of the art modern methods with more computing power. It's easier to use modern computers that can run faster with some new programming languages to do statistics and data analysis in a different way, to do things that weren't possible before. So that's really cool, and I think that could lead with NTEP to a lot more insight into this nationwide project that's done at different sites, different different dates. There's different rating dates and different rating people.
Yeah, that this is something that I haven't mentioned yet. That is, whenever we look at turf grasses, it is something that has seasonality. At different time of the year, it's going to perform differently. So we have to think about how to align, the visual rating skills at different time of the year and across multiple years, so that we present the seasonality of different turf grasses, to the ones who are doing study to them or who try to use them, so that we can, let's say, make a better mixing or blending to make sure that we have a long green cover, throughout the year, or really select cultivars and compare them at a given time of the year. Those are all the powers, of novel statistical model, can provide to our industry essentially. Yeah.
That that is very good. Because this is the ATC double cut, let's look at one of the blog posts on the ATC website, which I always try to pick at least one blog post from the ATC website and say, let's talk about it a little bit more. Let's explain why I thought that this was worth talking about. So I'm going to show now a blog post that at the top it says last updated on July 13th, which was yesterday, and the title of this, which I will put a direct link to this in the show notes. The title of this is Total Organic Material at the Surface of Cool Season Grass Putting Greens. This is related to the OM246 project, the measuring of total organic material by depth at the surface of putting greens. I think this is really useful as a way to evaluate the effect of your top dressing practices, the effect of your other organic matter management practices, and a way to figure out into the future how much sand top dressing you should apply, and to figure out if you should be applying more, if you could be applying less, because it's measuring something that you can't really see, but you can put an exact number to how much total organic material you measure. And I first wrote this post in 2020. I wrote it in October of 2020. And I said, I've collected a lot more data since then. And I've updated my Bayesian model that I used to generate a posterior distribution of what the expected values would be given the data that I've collected and given the model that I use to predict what the total organic material would be. So I said, let me generate those charts again. And then I thought, what better person, because I think that may be the first time on this show that I've talked about a posterior distribution of data. I thought, what better person to explain this than you, Henry? So let's look at this particular chart, which shows a random green of unknown species. The organic material is on the x-axis, so it's showing a density curve or the probability distribution function, and this specifically is the output of a Bayesian analysis. So I've given a prior information to the model. I've said that I expect the organic matter to be distributed in a certain way, and then I've taken measurements and I've told the model or told the computer that these are the measurements that I actually have, and then I've written a model that has a certain equation in it that says this is how I expect the data to be generated. The data should be able to be generated from this type of model that includes variables or factors such as the species of grass and the type of variability that we would expect to have for greens of different species, and an overall average, and an overall average for the effect of the treatment, the overall average for the effective species, and an overall variability term. So then I generate something like this, which I imagine when I share this on my blog or when I share something like this on Twitter to the general public, to golf course superintendents or turfgrass aficionados around the world, I imagine it could be something of like, what am I looking at? Their response might be, what is this? I don't know what it is. But I think that you probably know what it is, and you can probably explain it perhaps better than I can. And then perhaps by us both trying to explain it, and people hearing me explain it and people hearing you explain it, I think they might be able to understand a bit more about prior distributions, posterior distributions, and so on. Are you willing to have a try at explaining this, Henry?
I'll give it a try first. I'm sure combining the two of us, more people will be understand, what we are trying to do here. So
Mm-hmm.
I think,
Thank you.
let's think about how we just know the word in general. Usually when you try to learn something new, you already have some prior knowledge about the specific subject. But to learn more about the subject, oftentimes you need, in a scientific way, you need to conduct experiments. For you, Dr. Woods, you have to do some measurement in the real world to understand what is actually going on there, and then form your updated knowledge about the specific project. So this process, in general, if we were to describe it in a statistical way, is the Bayesian statistic way of doing things. That is, I have some prior knowledge, but in this case, we're going to call it a prior distribution, because we're going to have form some kind of knowledge related to a specific parameter in a distributional way. That means how likely it's going to show up for this value, how likely it's going to show up for the other value, and we describe those value in a form of distribution. And this prior knowledge and the prior distribution oftentimes comes from other people's experiments or literature, or uh, experiences, just life experiences. For example, I know for sure the organic matter is not going to be having a value between below zero. Once we have this prior distribution or prior knowledge related to a specific subject, in this case, organic matter, and then we go collect our data points from the real world. We go to different golf courses in your case, collect soil samples, do the analysis in the lab and get this number. And then now we have some existing data. We have some prior knowledge about it, and then we have some existing data about it. And these two combined together is going to update our understanding about this specific project. And combining these two give us what you have here right now, the posterior distribution or the posterior knowledge after we conduct the experiments. And this is exactly what we are looking at right now. That is a density curve for the organic percentage, once we conduct our experiences and learn new things about, organic matter.
Thank
Did
you
I?
for that. Thank you for that excellent explanation. I, I, I find this so fascinating because I didn't really know what density curves were. My background is as a greenkeeper and, taking care of grass. The type of math that I would do would be like calibrating a fertilizer spreader or calibrating a sprayer and figuring out water volume or figuring out how we're going to apply this product at so many kilograms per hectare or something, or, how much sand we're going to apply. Or, for the advanced type of math that I would do would be to figure out if you have a core, a hollow tine coring, and you have a diameter of 3/8 of an inch or 10 millimeters, something like that. How do you use the pi r squared formula to figure out the surface area of the tine, and then you'd figure out if you have the spacings at 2 inches by 2 inches or 5 centimeters by 5 centimeters, how many holes would you have? That's the type of like straightforward, elementary or middle school type of math that I was commonly doing. And to get into these kind of probability distribution functions and kernel density and these type of posterior distribution curves, it's something that I've learned later in life, but it turns out to be so useful and so interesting because, as you explained so well, this is the way we think. This is the way we learn. We have some amount of prior knowledge, and it might be very vague and very limited, but it's still something, and we can specify that. We could specify that we know almost nothing, but then it's going to the output of the model, the posterior distribution. If we say that we know almost nothing, then it's going to say, well, the data that you collected is that's the world. That is the output. That's our highest probability output. In this case, with the chart that is showing on the screen right now, which is the posterior distribution for any grass species, any putting green, it's not saying there's a specific species involved, and we don't know what the species is, so we just walk onto a green anywhere and sample it. The prior for this, the prior knowledge is from an article from 2005 from the author was Alex Glasgow and some co-authors. So it's Glasgow et al. 2005, I believe, from the International Turfgrass Research Conference or the International Turfgrass Society Research Journal. And it's about a survey of putting greens in New Zealand and what the total organic material was. And they had a nice table in there that presented here's what the normal values were for many greens that were tested in New Zealand. And that at the time that I started this project, I thought I knew something. I couldn't go into it and say that I didn't know what was normal. I knew what was normal. And I also knew in the UK, this is a type of testing that's been done in England and in Scotland and in Wales and in Europe a bit over the past 2 decades. And I knew that the values that were measured in Europe were quite similar to what was reported in this article from New Zealand. And so in the model, I use as the prior information that I have is that I expect the values to be something like they were measured in New Zealand. And then I add my own data to it. And as I put more and more data in, that data can start to overpower what the prior is, but there's still some prior information, some information that I knew before is still embedded in the output, and it's mixed together with what I with the data that I've collected. So I think it's just such a direct way of trying to attack a problem and trying to learn something. I really like it. And did you say you have a master's degree in statistics?
I did, yeah. Because my PhD was on tall fescue breeding specifically, and then we have to do a lot of such modeling. And as I approach, different levels of my study, I find it extremely useful, important for me to learn about statistics. So I later on, had a member on my committee that is a Bayesian statistician, and he taught me how to do such kind of analysis, and they encouraged me to take classes. It was a tough time at that time, and so I had to get up early in the morning, do field trials, work on different golf course, different tall fescue trials, fine fescue trials, and all that. And then at night, from 6 o'clock to 9 o'clock, I would go back to the classroom and to take my statistical classes.
Well,
So
it pays off, doesn't it?
that's true. That's true. I actually end up working as a data scientist. Although I still have a strong turf signature, but my daytime job is actually working more with the data rather than working with the tall fescues and fine fescues and all that.
Okay, yeah. Well, yeah. There's a high demand for that type of information because with the computing power that is available these days, I think that Bayesian statistics is nothing new. It was the Reverend Bayes. Was he in the 1600s or 1700s?
Yeah, it's been around for a long time. I think
Hundreds of years.
hundreds of years. Yeah,
And
but the problem is in the computation part. Bayesian statistics oftentimes requires a lot of computation, which was not available to us until the recent, 20 to 30 years. That's why you see a lot of activities in the Bayesian statistical world recently, because now we can address those computational issues, with much newer computer and cluster, computation. Yeah.
yes, it's not easy to solve those, and in fact, they aren't really equations that get solved. It's done by a Markov chain Monte Carlo, which is generating a lot of data, and then you make inferences based on a number of results. So you've got thousands and thousands of results in the posterior, and that you're then making inferences based on that. It's not
right.
like you're solving an equation and getting an exact answer.
Yes.
The way that I
So
understand it.
that is exactly correct. Oftentimes we have to do really complicated integration if we were to solve that mathematical equation. But those statisticians and mathematicians have designed smarter ways such that we don't have to do that mathematical calculation. What we do is we draw samples from the posterior distribution and test or reject that specific sample based on if it's actually fitting on our description or assumptions related to the posterior distribution. If it fits in that assumption or description, then we keep it. If not, then we reject it, such that we can generate a large volume of the posterior sample. And once we have tens of thousands of samples, then we can use it to effectively approximate the actual distribution without actually doing the mathematical calculation. But
Yes.
of course, you can see how this process can be computationally intense. Yeah.
Yes, and so this is interesting because it goes back to how many of the current generation of turfgrass scientists tend to do statistics and tend to present results. They've been trained in a different way of thinking about statistics, which is called a frequentist paradigm, and that something that I think the listeners to this, if you've been to turfgrass conferences, you've probably seen slide after slide that have something called LSD, and you'll see tables with data, and then you'll see something called a least significant difference. And in fact, that's how a lot of the NTEP data, I'm sure if you go to the NTEP website and you can look at the reports for various turfgrass species, various NTEP trials, and you'll see the data are often summarized with a LSD, least significant difference, and that is a frequentist way of thinking about whether something is significantly different or not, and that is the way that everybody's been trained. So people in the turfgrass industry tend to have been trained in that, and then because they know how to do work in that way, they continue doing work in that way, and there's not so many people that are doing the Bayesian analyses, which is something that it wasn't really possible to do that in 1995 with the type of computing power that people had. So when everybody was, I got my PhD in 2006, but I was still learning. I still learned ANOVA, which some people might have heard, analysis of variance, which is something that commonly is analyzed with specific treatment differences looked at as a least significant difference.
Yeah.
And I think people are still taught that because all the articles that they read is like, here's table 2 and ANOVA table, table 3 and ANOVA table. And I look at that now, I'm like, what are all these F values and stuff? It's meaningless. Why don't we just go directly at the problem? And I think for me, the Bayesian analysis is a way of just going directly at the problem. And then we can find, okay, we're 77%, 77% of the values are above zero. So if that's the case, then whatever we're trying to measure, we would say, or we're trying to predict, we would say we've got a 77% chance. If the posterior distribution says 77% are above zero, we've got a 77% chance that it's above zero. If it was in the frequentist way, they would just say, oh, it's not significant. But then Bayesian is more like, okay, it's not going to be every time, because 23% of the time you might be less than zero, but the weight of the evidence suggests that most of the time whatever we're measuring is going to be above zero. And if it's the the traditional way of doing statistics, you would just say, oh, we've got nothing there. But actually you don't have nothing there. You've got information that you can talk about coherently with a Bayesian analysis, with a frequentist way of doing data analysis. It sometimes we just kind of conclude nothing.
Yeah, well, in a sense, frequentist way, or at least in the hypothesis testing process that we learn, provide a yes or no answer, and then Bayesians come in and say, okay, we don't really care about whether it's significant or not. We just gonna give you the whole distribution, and then you can interpret the distribution using your whatever statistical level that you wanted to use. We don't really care about the p-value. We just give you the distribution that for the specific parameters that you are interested in. Going back to the ANOVA conversation, ANOVA also has been around for a long time. When Fisher started to think about the idea of a linear regression and ANOVA, I think the first paper that he published was in the 19 probably
20,
1913, somewhere.
yeah.
Yeah, somewhere around there. I couldn't remember, but it's been around for a long time, and we were taught to customize, to design our experiments in the same way, in the way that it fits to the experimental design, and so that we can follow the same statistical analysis process to that is designed for ANOVA. But the issue is that we have so much you know um, accidents or incidents happens during our experiments. It's not going to go exactly as the way it is. There are always going to be something that is happening, leading to the deviation of an experimental design that is different from that original experimental design. And then how do we go about addressing those issues? And the Bayesian provide a flexible way, that is, we can observe the data generating process, and then using specific parameters or design specific parameters to describe this process, so that we can develop a model, and then generating some samples, and using that samples to cross validate our original assumptions, and then iterating this process so that we can learn about new pattern, about new process, and creating knowledge and updating our knowledge that we learned from textbook by doing experiments. This is a very natural way to understand experimental science, from my perspective. This is why I find it so fascinating that I just keep taking more classes on it until until I can actually put it into application in my studies. Yeah.
Well, I'm impressed at the way that you explain it, because the way that you're talking about it and the way that I'm hearing it as it comes from you, it sounds like you're a professor in this field, and explaining how this works and cross-validating and updating and all of this stuff. But, I agree with you completely. I took a number of data analysis classes in university, statistics and some spatial analysis, special spatial analysis class where we looked at kriging and other procedures to look at spatial variability, and really interesting stuff. And I realized that if we're going to collect data, do experiments, and study things, we need to express the uncertainty involved with that. How certain are we that potassium is required in this case, or how certain are we that this fungicide is better than that fungicide for controlling dollar spotter? How all the types of things that we as scientists try to learn about and then try to share. We need to know how confident we are and how uncertain we are. But the problem is, with the frequentist statistical methods such as ANOVA, you end up designing the experiment so that it will fit the statistical procedure that you intend to use, rather than perhaps you fortuitously come across a very interesting data set, but you don't have a statistical procedure to analyze it. Or perhaps, as you say, you do the experiment and then a dog knocks over half of the pots halfway through it. And so or you have a hurricane or a typhoon or something happens, and things happen, and then all of a sudden some of the assumptions that are baked into the standard frequentist statistical methods that you intended to use, suddenly it becomes a problem. And and I kept hearing about Bayesian analysis and hearing about how it wasn't really intuitive at first if you've come from a different background of learning about statistics, but then you can learn about it. So I've bought books and watched various seminars and read a lot of blogs and done a lot of this analysis myself through trial and error, trying to figure this stuff out. And now it just makes so much sense to me that I would encourage, if you're a student or if you're interested in data analysis and just want to learn, after you finish your formal schooling, like I have, I would encourage you to look into Bayesian data analysis, because it's a really logical and honest way to do things. And I think one of the problems that we unfortunately fall into when using the frequentist statistics is we're trying to look for significant p-values, meaning you're looking for the probability that something's going to be less than an arbitrary threshold. So you set up these convoluted hypotheses, and then there's the idea that science is something that's falsifiable. So then you have the idea that, well, we'll make a hypothesis that we know is not true anyway. But it's not like Bayesian analysis where we're saying let's be very honest and say here's what we know, and then collect some data and try to update what we know. The frequentist way is, it tends to be like, let's make a null hypothesis that adding nitrogen fertilizer won't have any effect on the grass. Now, we already know that's not true, but we might say for the purposes of our experiment, we'll make what we call a null hypothesis that says nitrogen fertilizer has no effect on the grass. And then we collect data, and then we find that the data strongly shows that nitrogen does have an effect on the grass. And so we express how confident we are in that with a p-value. So you'd use the traditional statistical methods, and then you say, oh, our p-value was less than 0.05. And if the p-value is less than 0.05, that means you can never accept your hypothesis. You can never accept your alternate hypothesis. You can never accept, with frequentist statistics, you can never accept that nitrogen has an effect on the grass. What you're allowed to do is you're allowed to reject the null hypothesis. So you reject the null hypothesis, which was not realistic anyway, but your null hypothesis was that nitrogen had no effect on the grass. And then through some kind of convoluted way of reasoning, you indirectly are accepting that there's some weight to support that nitrogen does have an effect on the grass. Now, isn't that confusing? And there are reasons that you might do things in that way, but it's very confusing, and it's very beating around the bush instead of directly attacking the problem of, how much does nitrogen affect the grass? And with the Bayesian approach, it's just directly going at the problem that we're really trying to solve.
That's right. Another issue related to this is that there is a trend that we are only going to publish the experiments or the results with the statistical significance, which I suspect will actually leads to the results that we fail to report a lot of the useful data. We just leave the data somewhere. We don't publish them. We just think that they are useless. But it might be useless for you to publish this article, but it could be useful for other scientists to understand more about this procedure if they can adopt a better way to analyze that data.
And it also leads to what's called p-hacking, which is it's not usually done maliciously. It's just done, people do it without really thinking there's even anything wrong with it. Is they're like, oh, well, our p-value here was not low enough to reject the null hypothesis. Well, have you tried transforming the data? And if you transform the data, or let's drop those treatments, which you can come up with some reason of like, well, it was especially hot on those days, and the other days it wasn't so hot. So let's drop out the measurements from the really hot days, and all of a sudden our p-value drops to 0.047, which is below this arbitrary threshold. So now all of a sudden we have something that is significant, and because it's quote significant, now we can publish it. And
That's
and
right.
that's what
Yeah.
people do without really realizing it. I did that with some of my data with a chart in one of my articles that I'm not so proud of. Is I instead of reporting all the data, I did a regression on the average of the data instead of on the average of all the treatments. And so that gives a really nice R squared and a lower p value, and so it looks much better. But actually, I'm not. That was with snow mold, but there's no doubt that added potassium was making the snow mold worse. But and that's been duplicated by others at different locations and other scientists, and there's plenty of documentary photo evidence to show. But the p-value that I reported and the r-squared value that I reported in the paper that I published were inflated over the way that I would do it now. And the way that I would do it now is just say, let's be honest about here's all the measurements. And I would do a Bayesian regression in this case, instead of trying to fit the frequentist way and trying to minimize the p-value.
That's right. And then you can customize the process, choose the right distributions, for the, for based on what you have observed, or based on your intuition, your knowledge about this process. And you can customize the model, based on what you have observed in the field, so that it gives you more insights. It's going to help you get rid of the confounders, which you were not able to get rid of, using traditional ANOVA or linear regression methods. So there are really powerful customizations that we can do, based on the experiments that we or the measurements that we conducted. Yeah.
I want to show one more chart from that same blog post, and let's look at different species. So I'm showing now the posterior distributions for cool season greens. I've got bentgrass poa greens,
I
bentgrass.
haven't I haven't seen it on my side yet. Sorry.
Oh, thank you. It's there we
That's
go.
right.
Yep.
Yeah.
So I've brought up on the screen posterior distributions for the total organic material at the top 2 centimeters for 4 different cool season grass species that are used on putting greens: bentgrass and poa mixed, creeping bentgrass, fine fescue, and poa annua. And this is a chart that I generated yesterday, and there are differences between the species. The fine fescue, and this is where I think the model could be improved, and that's why I added something to this, is that's saying this is the date the plot was generated and with the model that I was using on a certain date. The fine fescue is very narrow, and if you think about it, it's unlikely that fine fescue is going to be only from like just 2% to 8%. There must be some fine fescue greens out there. Right now, the model is predicting that 90% of the fine fescue greens in the world are at 5.9% or less organic material at the surface. And probably there may be people listening here who have pure fine fescue greens who can confirm this, but you might be 7-8%. So that means the way that my model is written, I think I need to have a bit more, whatever I need to do, it needs to make fescue more uncertain, because I'm not as certain as the model tells me for fine fescue. Do you understand what I'm saying there, Henry?
Yeah, yeah. So it comes down to how much of a prior knowledge we have related to fine fescue. I'm curious, what kind of prior distribution or prior knowledge you have related to fescue samples, and also it's also related to how many data points that you have collected, or actually measured. So could you please provide a little bit more information on those two
Yeah.
factors?
So yeah, well, we'd have to dig into the program so that you could see exactly how I've written it. But I put the prior for every grass species to be the same, which is based on the Glasgow et al. Article from
Hmm.
2005, which is based on the New Zealand survey. So the overall average is expected to be about 6%. And then I measured fine fescue from, it's only from 2 golf courses, and the total number of samples is very low. It's probably, I think it's from 5 to 10 samples. That's what's in the data set right now. But all of those samples were right around 4%. So
Okay.
if we look at that, I can't zoom in on it, but the average here,
Mm.
or the 50th percentile from the posterior is 4.8%, which means there is some information coming into the posterior from the other, from the prior and from the other grass species, like I expect. It is moving up the average from what I actually measured. However, I just think that the tail here is, there needs to be more of a fat tail, because I have such a low number of data points. I don't want to be this certain about the prediction.
Got you. I suspect the measurement you got, I'm actually quite confident on this. The amount of samples you have on top fescue, they all have a very close value. That's
Fine,
why
fine, fine fescue.
fescue, yeah.
Yeah.
Sorry about that. And then that's why, and then you see a very narrow distribution. This
Mm-hmm.
is a reflectance of, it's a small but quite a uniform data sample that you have gathered. And originally you mentioned in the prior distribution the mean is around 6, and that's why
Mm-hmm.
it's shifting towards 4, where your sample mean are. And at the same time it's putting it's giving you, providing you a lot of confidence in a way where a distribution is narrowly centered around 4.8
Mm-hmm.
4.8. I'm sure as you gather more data from different golf courses or different location of the same golf courses, you will see the distribution started to get wider and wider. Right now, because you don't have much information provided in your prior distribution, and your data sample seems so your sample of your data seem so confident about this measure, because they are all somewhere around the 4 ish,
It
right?
was very well maintained turf at the Bandon Dunes Golf Resort in Oregon, on a
Uh,
couple of those golf courses, and it was very consistent. And you nailed it. It's exactly like that. And so
yeah,
all that the model knows is that it saw some data that was really consistent. And so
yeah,
based on that, it's saying, well, for this species, everything we know about this species is that the data that we have is this species is way more consistent than Poa
yeah,
annua, because for
yeah.
Poa annua it's seen from 3% up to 16% or 18%. So it comes out really good.
Like you said, the model is being really honest, to you. It's telling you what exactly you observed. But this is exactly why we need to combine, our human observation, our prior knowledge with the data, because we understand which one is probably should be assigned a higher value, in this process. Right now, the prior knowledge is definitely going to be more important, because we only collected a couple of samples from one golf courses. As you collect more and more data from different golf courses, our prior distribution, our prior knowledge is going to become less and less important, because we have known and learned so much in our experimental process. So at that time, that distribution is going to be a reflectance of the true value or the true distribution. Um, that's why I like a quote from a famous statistician, George Box. He said, all the models are wrong except some are useful. In this
Yeah.
case, you have situations. you have designed a useful model.
Henry, you were just freezing a little bit. You were just freezing a little bit. Can you restate that all about the useful models and just say
Sure.
that quote again, because I think everybody would like to hear that.
Yeah. So at the end of the day, the models are simple approximation of real life complexity. That's why a famous statistician, George Box, used to say, all models are wrong except some are useful. And in this case, congratulations, you have discovered a useful model.
well, thank you very much. And yeah, I think that's a great way for us to close. That is a good quote, that all models are wrong and some models are useful. And we shouldn't put we can't put too much weight into the model. We need to understand the strengths and weaknesses of the models, and be very honest about it, and then keep trying to improve. And that's something that I've really enjoyed talking with you about. So thanks so much, Henry. I'm glad that you're working on the NTEP data, and hopefully you'll be working on some other cool turfgrass stuff in the future.
So that's for sure. Yeah, glad to be here.
All right. Thank you so much. I will sign off now. Say bye-bye to you from Hong Kong, and bye-bye to everybody else around the world. I will be back again before too long with another interesting episode about turfgrass and turfgrass science. For ATC from Trang, Thailand, I'm Michael Woods.